long is the coast of Britain? This is a very famous question, but before I give you the answer, I want you to take a guess. Come on.
300 miles.
300 miles.
Very long.
Indeed, it's very long. In fact, you probably wouldn't believe me, but it's infinitely long. The reason why is part of a topic known as chaos theory. Chaos theory has many applications, including weather patterns, computing, medicine, and artwork. As someone who uses chaos theory to create computer-generated artwork, I enjoy studying the techniques and uses of chaos theory. Chaos theory is used in many ways and has already deepened the understanding of many scientists and researchers. I'm going to talk about what chaos theory is and what it studies, and some of the history behind chaos theory, and then some of the applications. So, what is chaos theory? Chaos theory studies any object that exemplifies three main points, three qualities, which I'll demonstrate using this double pendulum. First, all chaotic objects are sensitive to initial conditions. This means that small changes in the beginning become big changes later on. Were I to start the pendulum at any other location, its trajectory would be greatly different. This is also known as the butterfly effect, because a butterfly flapping its wings in New Mexico could create a hurricane in, say, China. Secondly, the chaotic objects have dense periodic orbits. This is a little more complicated to explain, but I'll borrow the explanation of Mark C. Carroll on his blog, Good Math. Mark says that the dense periodic orbits are similar to the planetary orbits around the sun. However, unlike the idealized ovals that we often think of, these orbits are more like the real orbits of the planets. The planets are being pushed and pulled by their moons and by the other planets, and each time they're pushed and pulled, they never quite come back to the same spot. In the same way that this double pendulum, when it passes a spot, never comes back to that same spot with the same velocity to repeat the same path again. These two qualities combine to form the third quality, unpredictability. We never know exactly what's going to happen next when we have a chaotic object. Now that we know a little bit more about what chaos theory is and what it studies, let's discuss some of the history behind chaos theory. In order to discuss that, I'm going to discuss two founding fathers of chaos theory, Edward Lorenz and Benoit Mandelbrot. Edward Lorenz discovered his chaotic object in the 1960s. He was studying meteorology, and he was using what we would consider an old computer to run a weather simulation. Due to a rounding error, he discovered what we now know as the butterfly effect, which he documented in 1963 under the title Deterministic Non-Periodic Flow. Benoit Mandelbrot also studied chaos in the 1960s. However, he wasn't studying weather. He was studying the stock market. He described stocks in ways that many modern chaos theorists would now consider descriptive of dense periodic orbits. Perhaps he's more famous for answering the question I asked in the beginning of this speech: how long is the coast of Britain? And using that discovery to launch into a description of his newest chaotic object, fractals. Now that we've covered a bit of history surrounding chaos theory, let's discuss some of the applications. There are two types of applications, abstract and practical. Let's discuss practical uses first, and then abstract next. The first practical use that chaos theory has is Edward Lorenz's discovery, the butterfly effect, which affects nature, such as weather patterns. A second use for chaos theory is in cryptography. According to George T. Yergin, 1997, from Columbia State University, cryptography is another use for chaos theory, because the chaos can be used to encrypt a message, which can then be decrypted using the same initial conditions that it was encrypted with. A final use for chaos theory is in medicine, because when in the face of a medical emergency that exhibits chaos, such as seizures, doctors can make use of dense periodic orbits. When the seizure begins to come out of a stable orbit into a more unstable orbit, doctors can intervene to nudge the system back into stable orbits, thereby stopping the seizure while requiring relatively little intervention. Now we have the abstract uses of chaos theory, including the answer to the question I posed in the beginning of this speech: how long is the coast of Britain? Now, Mandelbrot, when he proved that the coast of Britain was infinite, used chaos theory to redefine our knowledge of dimension to include fractional dimensions. When you have fractional dimensions, you get a scenario in which one-dimensional units, such as length, become meaningless. You can travel around Britain in, say, a battleship, and you can get one measurement. You can travel around Britain in a canoe and get a longer measurement, because you can enter the bays that the battleship cannot. When you walk on the shore, you get an even longer measurement. And if you take a microscopic probe, you can get an infinite measurement, because it entails going around every atom. And that's a lot of nooks and crannies to uncover. Now that we know some of the uses for chaos theory, let's conclude. I hope you've learned something about chaos theory and how it affects a broad range of professions and topics. We covered what chaos theory is, some of the people, the founding fathers behind chaos theory, and some of the applications for it. Chaos is everywhere. It's in weather, it's in biology, it's in some of our bedrooms, and it's also in art. Chaos theory, therefore, has many applications. For me, it can create art. For a doctor, it can stop a seizure. For you, there's a whole world of possibilities.
Have a great weekend!